So this is the fifth lecture in the series for um, Bioinformatics, Bio 410, Bio 510 for my class here at California State University, Monterey Bay. Today we're going to be talking about philosophy, interestingly enough, but more importantly, reasoning. And I think it's important that we think about how we approach questions and ask questions, especially as in this course we begin to delve deeper into the usage and implementation of statistics and models. A very important component of accomplishing bioinformatics. And, a lot of these questions about reasoning you might thought would be settled, but big data, bioinformatics, computational approaches have all had a big effect on how we approach science. And so it's all actually not as straightforward as one might think. So I think it's important for us to think about this so that we can be better scientists. I'm not dogmatic about any kind of specific philosophy, but it's good to know where things come from and actually think about why we believe the things we do. So, first question is, how do we do science, right? So we talk about science, and we're talking about bioinformatics, which is at its heart based upon methodology. What are the methods we use? So, if I had to ask you, look, how would you do science? Probably most of you would say something like, oh, we use the scientific method, right? And I'd say, well, what's the scientific method, right? Because I'm an argumentative professor. And you get something like, oh, you got to ask a question, then I'm going to construct a hypothesis, then I'm going to test with it. I'm going to test that hypothesis with an experiment. I'm going to collect some data. I'm going to evaluate my data. And then I'm going to figure out whether or not I was able to get results that align with my hypotheses or some that don't align with my hypotheses. So am I rejecting my hypotheses or providing support for an alternative hypothesis, right? And we all kind of understand this as a process we all should be fairly familiar with, that we learn early on in our education as scientists. But we might want to think, where did this idea come from? Like, we just kind of accept this as, this is the scientific method, right? Well, where does it come from? And more specifically, why does it matter? Why is this the trope? Is this the model of thought that and the model of practice, right? This is a methodological practice that we use within the sciences, and why is it so widely accepted? Right. If we had to think about where it comes from, it's got a lot of its roots in the philosophy of naturalism, specifically in a branch of naturalism that's referred to as methodological naturalism. Philosophy of naturalism, or methodological naturalism, basically seeks to explain the world around us based on what we can observe, test, replicate, and verify. Right. That comes from an old court case, its definition. And I think this is important to understand because if we think about these roots of naturalism, they go all the way back to Aristotle, and then Spinoza and Hume and Kuhn and Papineau and Gould. They just keep on going on through the ages. There's lots of ways that naturalism has these concepts and precepts of naturalism have been invoked for us to understand the scientific method. You might ask yourself, okay, but philosophy, we're really going to be talking about philosophy? Is it really that important? Well, I kind of feel like it is, right? Because when we talk about philosophy, what we're thinking about is the study of the fundamental nature of knowledge, reality, existence, and especially when it's considered as an academic discipline. And so if we're talking about the philosophy of science, right, we're talking about a specific discipline, we might want to think about, well, what is science, right? Science we could define as the systematic study of the structure and behavior of the physical and natural world through observation and experiment. And what you can kind of see when you start to combine these two things, right, the philosophy of science, thinking about the fundamental nature of science, and then looking at its structure, studying its structure and behavior of this natural world, right? We start to get to this idea of the philosophy of science. And what is the philosophy of science? It's going to be the theoretical basis for science. And all of this points back to those ideas of naturalism that I pointed out on the last slide, right? Where in that case, we were looking to seek explanations in the world around us based on what we can observe, test, replicate, and verify, right? And here we can see that these are the types of theoretical basis for how we conduct and execute science. And so, going through this process, it's, I think, important for all of us to think about, right? Do we adhere? What do we think about these ideas? How do we practice these ideas? So there's a good stats book by Quentin Keough, and in it, I pulled a quote from it that says, a fundamental step in becoming familiar with data collection and analysis is to understand the philosophical viewpoint and basic tools that underlie what we do. So if you really want to be, I think, like a very thoughtful scientist, it is important that you understand like why you are doing the things you're doing. Like what is the origin and method that you're applying to different cases, because to be honest, there is no perfect approach. And it's important to understand the limits and strengths of different approaches and perspectives and philosophical viewpoints, as well as tools, as we go through and try to accomplish science. All this stuff will eventually lead us to the question of, well, why do we need statistics anyway? But before we get to that point, let's talk a little bit more about the scientific method. So, thinking about the scientific method, one of the things that was sort of important is to consider in this process of the scientific method are the different types of ways that we reason, right? And so inductive reasoning, which was brought about sort of like first promoted through Francis Bacon and then others like John Stuart Mill, right? And this is an idea that when we're thinking about inductive reasoning, so reasoning inductively, what we're doing is we're drawing conclusions that we consider to be likely, right? And we're doing this based upon inference. And basically what we're saying is that we think there's a good reason to accept B given some observation A, but it's not a necessity for it, right? And how this works is we usually have a sufficient number of confirmatory observations, or observations of the natural world, with no contradictory observations, right? And this allows us to conclude that a theory or law is supposedly quote unquote true, right? And there are some issues with this type of approach. One, it's basically logically it's difficult to say that there's ever there's no amount of confirmatory observations that can ever prove a theory, right? So that's when all we find is yeses that never says that a theory is true. And then there's this famous quote that you'll often hear in scientific circles, attributable to possibly Martin Rees, which is the absence of evidence is not evidence of absence. So, an example of how we might inductively reason would be something like, well, what we have seen is the ability of these cells to feed the blood vessels of tumors and to heal the blood vessels surrounding the wounds. The findings suggest that these adult stem cells may be the ideal source of cells for clinical therapy. For example, we can envision the use of these stem cells for therapy against cancer tumors, blah, 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 right? So here we have these positive confirmatory observations that lead us to some sort of theory or hypothesis, right? We don't have anything rejecting this. We have nothing to suggest that it's not true, right? So we're going to hold it and think that it could, that evidence suggests that this is true. On the flip side of inductive reasoning, right, we've got deductive reasoning. And the grand poobah of deductive reasoning is Karl Popper. And this was this idea of conclusion guaranteed, right? And in this case, the idea is that instead of the previous case, right, where there was good reason to accept A given B given A, now we say B is the logical consequence of A. Oh, sounds so much stronger, right? Sounds a lot better. I feel more confident. This is the process of deriving explanations or predictions from laws or theories. And the deductive reasoning approach is based upon the principles of falsification, right? This is a big part of Popper. Popper actually was not, when he talked about naturalism, he was kind of negative on it. He saw naturalism as being very inductive, right? He saw falsification as being the key part of the scientific method, right? Even if we were basing it on the natural world and observational stuff, this was the part that told us the evidence that this was the least biased way of thinking about evidence. And so in this process, right, we had theories or hypotheses that are disproved because some sort of evidence proves that it's logically impossible, right? So in this case, all hypotheses are falsifiable if they you have to have a falsifiable hypothesis. So there has to be a logical possible observation that might be inconsistent with it. So you can't build a hypothesis that's not falsifiable in this instance, right? And by examining these hypotheses and falsifying and trying to see if you can falsify hypotheses, that's how you can deductively reason that your alternative hypothesis is supported, right? And so we can think of it very simply that, if you have some sort of given like x equals 4, and if y equals 1, then 2x plus y equals 9. That's the idea, that's how logical we're going to be, right? It's a logical consequence. So an example we might use here is medical technology ought to be funded if it has been used successfully to treat patients. Stem cells are being used to treat patients successfully in more than 65 new therapies, right? Adult stem cell research and technology should be funded. That's the deductive case, right? We're using if X and if Y, then we should get this answer, right? That's sort of the kind of reasoning we want to see. And of course, like, you can see how this sort of example can be, can be a little bit in the eye of beholder sometimes, depending upon how we define our evidence and hypotheses. But very strong method. This is at the heart of the scientific method that we all know and love. Last one I'll talk about is abductive reasoning, right? And this Charles Sanders Peirce was a big proponent of this. And this is, we can kind of think of this as taking your best shot. So here we might infer A as an explanation of B, right? So A is an explanation of B. And this often comes from some sort of incomplete set of observation and proceeds to the likeliest possible explanation for that set of observations, right? This process can really be helpful in sort of like daily decision making. Using the information at hand, even if that information isn't complete, right? So, given some set of symptoms, what is the diagnosis that would best explain most of them, right? Juries hear evidences in a criminal trial, they must consider whether the prosecution or the defense is the best explanation, right? And so, in science, I would say that we have historically not necessarily taken the abductive approach. We tend to go in a process where we start with the inductive and we go to the deductive, and then circle back around to the inductive and go to the deductive. So it's like this circle of different reasoning approaches. If we think about like what this looks like in terms of the scientific process, right? Scientific process classic, if we were to say, and we think about that that diagram we had at the beginning of how the scientific method works, right? First, we're going to start off, we're going to use our inductive reasoning to identify pattern, right? And to form some sort of ideas or conceptions about what that pattern, how to interpret that pattern, what's causing that pattern, right? That for which we find no evidence that suggests that that's not true. So we're going to develop some models of thought, some models of thinking, some models of explanation. And then from those models, we'll develop hypotheses, falsifiable, testable hypotheses. And then we're going to go out and we're going to do some experiments. We're going to test those hypotheses to see whether or not what we've come up with in this model is actually supported by experiments and data. So, pattern description. Again, pattern description is inductive. It's often comes about through observations of pattern or departure from patterns in nature, that things that we see, ideas that come to us, personal experience, or experience with the literature or something like that, right? We have some sort of process or pattern that we've used to identify through data analysis, even could be, right? When we look at, you guys will read this Underwood paper, in this 1990 Underwood paper, these things come up as we think of them as puzzles or problems, things that sort of catch our eye. And these are our inductive processes. And this is a really important part of the scientific process. Okay, let's not discount what this is. This is the observation. This is your walk in the woods. This is this is Bob Payne looking at the intertidal and thinking why, when I see all of these sea stars here, does this community look so much different than the one without sea stars, right? This is where you start to formulate your hypothesis or your model or theory of thought, right? And so the models that we come up from after observations, we try to figure out, well, how am I going to explain these observed patterns, right? What series of statements could explain what I'm seeing? Why does this community look so different where there's these sea stars, or look so different, and why than this other one, right? And maybe it's because there's sea stars in this one and there's not in the other, right? So I start to think about, well, what's that model that's driving it? How can a whole community be affected by it, right? Well, maybe there's an important species, a keystone species that's driving this process, right? And so this whole thing kind of comes from an interaction between, inside, your previous observation, existing theory that might be out there, and also in some ways personal belief, right? So it's a very organic process that involves a certain amount of creativity and intellectual acumen to be able to take all these different things and process them and think about different ideas. And this can be a really exciting part of the scientific process. And I would say there's kind of three types of these models that we might come up with. Historically, there were lots of verbal models, and so these were sort of non-mathematical explanations for how nature works, and I think these were particularly obvious in a lot of biological systems, intermediate disturbance hypothesis, things like that, right? These verbal models, which make a lot of sense, right? They're based upon pattern and explaining pattern, right? Then there are also empirical models, and these were, very explicit mathematical descriptions of relationships, right? These were how specific relationships, it would describe how one process is related, is driving something rather than another process, right? These were often statistical, and they would have responses and predictors, right? Suddenly we see that, the application of math here adds, a little bit more boundary around our hypothesis, but also may open up the area for being a lot easier and clearer to test. And then lastly, there are theoretical models, and these are used to study process. So we might think of these as less mathematical, less equation-driven, and more statistical. So here we're looking at what are the processes that are driving something. And so, we're thinking about distribution. So, what's the spatial variance in snail abundances caused by variation in settlement of larvae? How are these distributionally statistical processes driving pattern rather than, say, an explicit mathematical relationship? So after we have our model, we are then going to think about how we might actually test our model, right? What's our hypothesis in our test? And here, what we do is we say, well, we've got these predictions that we would actually deduce from these models. If these models are true, then we would expect to see these sorts of research or logical hypotheses. So if the model was correct, we would predict a certain set of observations, right? And then we're going to use some sort of critical or formal test to evaluate those models based upon that predicted set of observations. And to do that, we need to create a process by which we have hypotheses that we can falsify. in this case, it's important to note that we're never going to prove a theory, that it's logically impossible to do that. But we can show that there are no hypotheses that could falsify that theory. So how do we pick these hypotheses or test? What we have to do is we have to have a process of falsification testing, right? And the classic way of doing this is we have a null hypothesis that includes all the hypotheses except for the one that would be predicted by by the hypothesis you put forth or your alternate hypothesis, and you would go through and try to disprove your null hypothesis, right? And so in that process, if we're going to test this experimentally, we would reject our null hypothesis, and then our alternative hypothesis would then be our logical hypothesis, and that alternative hypothesis would be supported as well as the model that it came from if we can reject our null hypothesis. So it's this process by which we're looking to reject the null hypothesis. And if we can't reject the null hypothesis, then we are not finding support necessarily for our alternative hypothesis or model. So falsification is a really important concept and approach in the scientific method. There are alternatives to it, right? And there are a lot of criticisms of falsification, right? So there are people who say that, if falsification is all we're doing, then all we're really doing is just refinement around existing paradigm, right? And every now and then we'll get something big, but for the most part, we're just stuck like in this endless cycle of, hypothesizing, testing, hypothesizing, testing, hypothesizing, testing, and we're never going to make any big jumps. Right? And this becomes problematic. Like, is that good? That the fact that we're doing that? Yeah, it's rigorous. It's certainly rigorous, but is that the best way to conduct and do science? To understand the natural world, to use the evidence of the natural world around us to understand it better? And then there are other people who would make the argument, there's a lot of individual decisions that are involved in creating and falsifying hypotheses that are somewhat risky and arbitrary. And, when we're going to stick to this paradigm, what that means is that we can never look at other hypotheses, right? We're always stuck looking at this null alternative framework. What about if there's multiple competing hypotheses in that we can't just look at one over another? We can't look at this in this strict Popperian way, right? We can't look to see if this hypothesis might be a better alternative hypothesis, right? If they're not mutually falsifiable, right? So there are all kinds of ways where we can come up to see if there's shortcomings and a need for some sort of alternative to this falsification process. There are some ways to deal with this. Corroboration is a really useful and important way to think about this. What happens when hypotheses passes a severe Popperian test, right? Like this really strict Popperian test. Well, for a strict Popperian, it only measures the past performance of a model. It doesn't allow for prediction in other circumstances, right? So, we end up with this really difficult situation where even when we're looking at rejecting a null hypothesis, it only actually, for a strict Popperian, only applies to that one experiment. So then it becomes impossible to corroborate, because even if we were to repeat or do something else, there could be all kinds of reasons why it might not apply to that specific case. So it becomes really difficult to sort of defend this sort of very strict approach to it. Not that it's not powerful, I'm not saying that, but there are some places where we might not think it's the best approach for conducting science. So what are solutions? How could we actually effectively corroborate the scientific process, right? And I think it's important to think about corroboration, because we're talking about testing things in multiple places to show a similar outcome, right? The repeatability and replicability of science is a really implicit and important part. If we want results that are going to be meaningful in a broader context, then they have to be demonstratable in multiple contexts. So something to think about here is there a place where we could actually allow for all of these different types of reasoning to exist and to complement each other. And I would argue that there is. Like, I'm not strict on any one of these things. I think that these are tools that are all in our toolbox. We use them all the time as practicing scientists, right? We're not as philosophically rigid as maybe we have been in the past, but there are good reasons why, because we can see the limitations of just taking any one of these approaches. So when we talk about corroboration of hypotheses, it may require some measure or some sort of assessment of whether or not we think like one idea is true or not, right? And so notice that when we think about this, when we start to build in these other structures, we have this idea of, well, I may not be able to strictly reject something, but I could say, most of the time it's not going to be this. Or I could say, like, objectively, like, given the evidence that I have, like, this is probably the best hypothesis versus these other ones, right? So there are ways that I can start to build in these structures, but notice that there's going to be some uncertainty in that process. And because there's uncertainty, we need to start thinking about how we might apply things like statistics. Now, there are arguments that some people have made that, all this talk about scientific method, it doesn't even matter anymore because we've got big data. And if you're a bioinformatician, you might feel that way. And that's your prerogative. You could feel that way. We've got AI, we've got machine learning, we've got all these different ways where we can just blast everything with data, right? So it's over. Who needs a scientific method anymore? We'll just collect data till we are done collecting data, till we can't collect anymore. We're going to be able to identify, like, using really complex data sets and algorithms to do this stuff faster than we could ever model it. So what's the point of doing theory? Like, why? We'll just go straight from pattern to result, right? We don't even need to do all that other business, right? Why waste our time with models and hypothesis testing, right? And the cool thing about big data approaches is that, like, we can apply this to any type of discipline, right? It doesn't matter. If things are complex, who cares? If it's too complex to be modeled, who cares? We have all the data. We have all the information, right? One of the shortcomings of approaches like inductive reasoning is that you could never sample everything. So say, like, you saw that there, all you ever saw in your life were white swans, right? And you might say, well, I think all swans are white. I conclude that all swans are white. And that's my theory, the theory of white swans, right? But if I ever see one black swan, then my theory's gone and dead, right? But assuming I had seen every swan in the world and there were no black swans, then I would be probably, I could make an argument that I'm right? So this is the case for this, right? Like, I can see everything. I can see all of it. And the other really great thing about big data is it allows us to make really fast decisions, right? So talk about business, politics, like we talk about, people using Facebook data, all the ways that people have leveraged social media in marketing and politics and all these other ways, right? Like, there are so many ways to apply these things so quickly using data, right? But there's a fun little article by Suchi and Caveni in Philosophical Transactions of the Royal Society of Mathematics, Physics, and Engineering, where they talk about this stuff, and it all addresses these ideas because there's been some talk about will big data be the end of the scientific method, and their point is that, well, I'm not so certain about that because a lot of complex systems are strongly correlated and they don't adhere to a Gaussian statistical model. And why is that important? The important part about that is when we talk about Gaussian statistics, right, we're talking about statistics that would adhere to some sort of like central limits theory or some sort of law of large numbers. And that just doesn't always apply in these cases, right? And, we can also think about data in that there are no data that are big enough for systems that are really insensitive to data inaccuracies. So if we're basing everything on data, how good is the data that we're getting? How biased is the data that we're getting, right? And if we don't have a good way of understanding that or how we're interpreting that data, like, it's been well documented that there are lots of ways that algorithms are biased. Just look at facial algorithms and how it treats different racial groups, right? There are ways that people have known for a long time that violate this idea that data is neutral, right? And so, if it's not accurate, there can be strong sensitivities to that, right? You're going to be misidentifying people as in ways that is really detrimental to their civil rights. So, this is an important concept to sort of get right if we're going to try to apply this widely, if we're going to subvert this process that has been pretty effective for us over long-term periods of time, right? And also there's this idea that, it happens, we talk about it all the time, but like correlation does not imply causation, right? So if we think about the link between two things, right, it becomes harder and harder to see the more data we throw at it. And what can happen is, we have a finite capacity to observe something, to see the truth, the thing that connects two things, that explains something, right? That's what we want to understand. What's the connection of the thing we want to explain? Because if we're treating a disease, we want to treat the cause of that disease. We don't want to treat the symptom. And what we have to be careful in this case is that when we get too much data in, we can just obscure the reality. And what we end up is just this exercise in curve fitting, where we're getting a really good job of fitting to this curve something that we think is right. But if the curve is not the right model, is not the right representation of what we should be looking at, we've sort of pointed ourselves down some sort of pathway that a data inaccuracy has identified for us, it could cause us all kinds of problems. So in the end, I don't think it ends the scientific method, but I will say that there are some ways that big data could help. These authors posit that non-linearity, non-locality, hyperdimensionality, really difficult mathematical, statistical, computational problems can probably be addressed with big data in a way that we've never been able to do before. So there's purpose and value in big data, no doubt. But there is, I think, still value in this scientific method, in understanding the causality behind things, and understanding and designing hypotheses and experiments to test things. So that brings us to the idea of testing. And we can see that, as we go into natural systems, especially life science situations, right, there's a lot of uncertainty in how we might test something, how we might examine something. So, we want to be able to actually have an application of detection and description of pattern, and we want it to be rigorous. Like when we do this, when we examine things with the scientific method, we want confidence in what we're doing and in our testing, right? And one thing that we have to realize is that when we take under experimental processes, the design and the analysis of experimental tests is really one of the most crucial steps. And it's really important to understand that like a research hypothesis is not necessarily the same thing as a statistical hypothesis. So me rejecting a hypothesis or falsifying a null hypothesis is not the same thing of confirming my research hypothesis or supporting my research hypothesis, not necessarily. So one thing that's really important, and the value that statistics can provide us, is that it's going to provide us with a very nice logical, mathematical, quantitative way of giving us a more complete presentation of the possible outcomes of our information, right? And what this does, it provides us with a good and convincing argument based upon some sort of evidence for our decisions about whether to accept or reject hypotheses or favor one hypothesis over another, right? And it helps us be aware of biases that might be affecting our data. And this, when we do statistical analyses, there can be biases that just affect our design, right? And when we think about like what's out there, so there can be theory tenacity, right? This is the case where like certain theories we might propose various hypotheses based upon theory tenacity rather than like our sort of reading or real inductive view of the pattern that's in the data. And also when you read in the literature, you might be more prone to come up with or favor different types of hypotheses based on the fact that, a positive result is going to be published more than a negative result. So, that rejection of that inability to reject a hypothesis may sort of bias you in some ways against certain types of argument. So just to be clear here, right? I've talked a lot about data and all these other things, you might have heard me kind of like, as a bioinformatician, it's really easy for me to poo-poo experiments. Experiments are important. They're really, really important, right? I'm just gonna say that right at the bat. Like, it's really important. Like, experiments are incredibly powerful. Classical approach, right? We're gonna devise some alternative hypotheses. We're gonna have this crucial experiment, which is gonna exclude one or more of these hypotheses. We're gonna carry out that experiment. We get a clean result, right? We can then recycle that procedure for new hypotheses and refine. And that is such strong inference, right? So when we do experiments, we can get really good, clear evidence of the kinds of things that we're trying to test. And that's how we can move beyond sort of these observational pattern processes of observation and correlation to something that's more closely tied to causation, right? So that's what we want to get to. Eventually, as scientists, we want to get to those mechanistic understandings of how things work in the life sciences. So this is a costly endeavor, though. Like, experiments always involve typically some sort of artificial manipulation. So is that really natural, right? When we get to large scale, is it even possible to do a good experiment? Can you actually accomplish that? Like, if we're thinking about ecosystems, how do I do an experiment? How do I perturb an ecosystem here and run a control somewhere else, right? Like, those are ethically complicated and maybe logistically impossible. So, it's important to think about that. And then, you also want to think about, okay, I did this experiment, but is that actually applied to any other system, right? So if I design an experiment that's really specific, really, well designed, it's intricate and impressive, and everyone compliments it, but then, like, you couldn't really apply it to the system. Is it really useful, right? Is it really applicable? And there are alternative ways for us to approach this as a term in terms of just like this classical approach of hypothesis falsification. And so there are ways to sort of like say, well, can I confront competing models with observational data, right? How well do the data meet the predictions of these different models? And it's an excellent book by Hilborn and Bangle about this called The Ecological Detective, which talks about sort of like, can I explore the likelihoods of different types of models given the data that I have, right? And so in some cases especially ecological cases where we have so much information, it may be difficult for us to do experiments, but easier for us to take this other approach, which feels a lot more like an abductive approach, right? Of things. And part of the power of inference and the power to deal and convince people about your evidence has a lot to do with sort of the nature of the data that you're using to examine these things, right? And so if we think about it, biological data is typically, a collection of observations of objects somehow that are related to the life sciences, right? And in it we have sampling units or experimental units. We might have sets of observations or that are a proportion of the total. We're not sampling all the forests, we're just sampling, these certain regions. So we end up with this like a representative sample. And hopefully, like, we're thinking of this sample is representative, so it's just like a random piece of like what everything else that is out there. And if we might describe it as either like discrete or continuous data, like it's a trait, is a continuous thing, is it something you either have or you don't have. And whenever we're going to be doing that, that means when we're collecting this data, we actually have some sort of level of uncertainty in the thing that we're collecting, right? And, I think that as we go through and we look at all these different characteristics of like the actual data that we might use to examine hypotheses, we can see, that when it comes to biological systems, especially because of this uncertainty component, that using a statistical, especially a probabilistic framework to describing these systems is going to be really important for us to put it in the context of in a mathematical, empirical context that we can use to make quantitative, defensible argument. So whether or not we're doing inductive, deductive, or abductive reasoning, it's going to really help us to place it in this framework. So probability is going to be really important to us because biological data is filled with uncertainty. Anytime you measure anything, you could possibly get two different answers. Why is that? Well, because when any sample that you're going to get, you might have some process uncertainty in it, right? Like you could see true differences between two samples, right? And that's a real thing. Like I sample from this population, I sample from this population, and they're different. Like these guys are bigger than the other guys. It just is. And that could be true. But I also could see a difference between two populations from when I get two samples just because I only collected 5 individuals twice, right? Instead of 500. Right? And if I'd gotten 500, they'd look about the same. But if I only got 5, they're going to look different. We refer to that as observation uncertainty. So the whole point of this is just to say that there's true differences here, and then there's some uncertainty in this process. Right? Did you do enough to actually say something about what's true? So how do we deal with that kind of uncertainty? We deal with that uncertainty using probability, right? And we're going to talk a lot more about probability in the next couple lectures. But in this case, I just want to be clear. Probability is the measurement of the likelihood that an event will occur, right? So on a scale of 0 to 1, that's what a probability is. How likely is it to occur? If it is 0, then it's not going to occur. If it's 1, then it will occur, right? So if we say the probability of A is 0, then it's not going to occur. And you know, you've all taken science classes before. I'm sure you've seen it. Like if we're to think about this, where this might come into play, so the most obvious case might be in our discussions of p-values, right? And so we have these sort of possible outcomes from a classic falsification experiment, right? Where we've got, you can either, you have a null hypothesis, it's either true or false. And after you do your experiment, you can decide to either reject or fail to reject your hypothesis, right? So what happens is that, say your hypothesis is false and you reject it, right? That's a true positive. That means that you got the correct inference. Same thing if your null hypothesis is true and you fail to reject it, right? That means that it was really negative and that's what your decision about your null hypothesis was. However, there are these two instances where you might have made a mistake, where your null hypothesis is true, but you rejected it. That's a false negative. And then you've got a type 2 error where your null hypothesis is actually false, but you failed to reject it, right? And so this is the case, like type 1 errors, we might refer to this as like, someone who's innocent getting shown to be guilty, whereas the type 2 errors are the case where, someone who's guilty is not found to be guilty. And so if you think about this, you guys have all probably seen a p-value at some point by this time, right? P-values are measures of type 1 errors, right? They're going to tell you, that's why you want your p-value to be low, because you want a low probability that the null hypothesis is true and you've rejected it, right? This is a conservative approach to science. Power of the experiment. So how much power do I actually have to reject a null hypothesis when it's false? Which is also a really important component of when we think about experimental design and how much inference a study might actually have. So that's all well and good, right? Experiments, statistical frameworks, very important. And statistics will apply to a lot of different type of reasoning types. But you can see how, when we think about experiments, that sometimes other types of reasoning may be important in our process. So, say we take an example, a classic sort of Popperian example when we think about like old growth forests, right? So if we think, oh yeah, wildfires, what are their effect on bird populations there? Well, wildfires, they don't affect them and they do, right? A very simple general hypothesis. Well, first of all, this is just an unrealistic experiment because no one's ever going to allow me to go out and just start burning old growth forests in paired examples as a valid experiment, ethical experience to see how they affect, endangered bird populations. That would be uh, not likely to happen, right? And additionally, okay, we could say, well, what if it happens naturally? Like, there's natural experiments, something burns. Well, is that really the same thing as an experiment? Like, is the context the same? Do I really have a control and a treatment? Is it equal? Do I have replicates? Can I show that it happens in more than one case? What if it happens in 2 different years? Well, the weather was different the year before. Does that matter? And so does that affect how much inference I have when I try to apply this strict deductive framework? So there are some questions that we have to think about if this doesn't happen. Like, is this even a valid way to think about this? And the same thing is, these aren't the best hypotheses I've ever come up with. It's a very simple example, but even if you reject that null hypothesis, then so what? So it affects wild birds. In what way? And how? And am I ever going to be able to do the experiments to show that, to really demonstrate that, right? And so, I just want to say, there are just questions out there where if we only take a deductive approach to it, it can just feel pretty unsatisfying. And it may not even be the most appropriate and informative way to frame and think about that argument. So inductive approaches, abductive approaches, especially in a data-rich world, in a big data world where we've got a lot of information, may allow us to sort of tease apart some of these more complicated and complex ideas. And what you'll find as we go through, and I think in this class, you'll find that there are lots of cases where different types of reasoning can be applied to very strong effect. And I think it's important to understand that they're all part of our toolbox, right? It's not just the quote-unquote scientific method. There's a lot of different ways for us to think about data in a rigorous, evidence-based, quantitatively reasoned framework that can allow other people to both critique and examine our ideas and hypotheses in substantive and meaningful ways.